We now consider the generalization of uh, the Newtonian law of gravity to the curved spacetime, and we will end up with the Einstein's equation. We need to obtain a field equation involving the metric tensor, which in the Newtonian limit gives the Newtonian equation for the gravitational potential, which was del square phi equal to 4 pi g times rho, where phi is the gravitational potential and rho is the mass density at the point R. Now we have already seen in the Newtonian limit of the geodesic equation that phi is related to the metric tensor. It's given by the following equation. G44 should be equal to 1 plus H44 in the Newtonian limit. And if we want to generalize this equation to the case of curved spacetime, then this phi should be given in terms of the metric tensor. And therefore, del square phi should be written in terms of the second derivatives of the metric tensor. And on the right hand side, we have mass density. And we already know in special theory of relativity that mass density can be given in terms of the energy momentum tensor. We now note that the Einstein tensor given in terms of the Ricci tensor and the Ricci scalar and defined as G mu nu equal to R mu nu minus half delta mu nu times R, and this involves the curvature tensor. So R mu nu is obtained from the contraction of the curvature tensor, and hence it contains the second derivatives of the metric tensor. So if we want a generalization of the Newtonian equation for gravitation, on the left hand side we have seen that it involves the second spatial derivative of the gravitational potential, and since gravitational potential is related to the metric tensor in the Newtonian limit, we also expect a generalization of this equation should involve second derivatives of the metric tensor. And we also know of a tensor called the Einstein tensor, which involves the Ricci tensor and Ricci scalar, and the Ricci tensor involves the contraction of the curvature tensor, and the curvature tensor involves second derivatives of the metric tensor. Further, the Einstein tensor given by this equation also satisfy a Bianchi identity, which is R mu nu minus half delta mu nu times R, then semicolon mu, where semicolon mu correspond to the covariant derivative with respect to x mu, and that should be equal to 0. And further, we can take inner product of this equation. This is a tensor equation. This object is the Einstein tensor, and this is a covariant derivative of a tensor, and therefore the result is also a tensor. So this is a tensor equation, and taking the inner product of this equation with G mu nu, we get with G nu eta, we get G nu eta, then R mu nu minus half delta mu nu R semicolon mu equal to 0. Now the covariant derivative of the metric tensor is equal to 0. And therefore, as far as covariant derivative is concerned, this is a constant. So this can be taken inside the brackets, and covariant derivative can be taken afterwards, after taking the inner product of G nu eta with this object. So when we do that, we get the first term G nu eta R mu nu minus half G nu eta delta mu nu times R, then the covariant derivative with respect to mu, and that should be equal to 0. But we already know that this object is equal to R mu eta. So that's the definition of R mu eta, which is obtained by raising the index of R mu. So this raises this index and will make it R mu, and the second index is raised and becomes eta. And over here, this involves an inner product with Kronecker delta. So that means nu has to be replaced by mu. So that will give G mu eta. So the result is R mu eta minus half G mu eta times R semicolon mu is equal to 0. Now in the flat spacetime, the energy momentum in the absence of external forces obey the conservation equation, which is given by T mu nu comma mu is equal to 0, because the force term on the right hand side will be equal to 0. Now we choose geodesic coordinates in which the Christoffel symbols are 0, and in these coordinates we expect the equation governing the energy momentum tensor in the special relativity to be valid as well, because the Einstein equivalence principle says that the laws of physics in the curved space-time should reduce to those of the special theory of relativity in inertial coordinates in small enough regions of space-time. So we can choose geodesic coordinates, and in those local inertial coordinates, the energy momentum tensor should satisfy the same equation as in the special theory of relativity, which is this equation. And energy momentum tensor over here is the one that is defined for the curved spacetime, but now written in geodesic coordinates. Now in geodesic coordinates, we know that the Christoffel symbols gamma, mu, alpha, beta are all 0. And therefore, the covariant derivative reduces to ordinary derivative. So in geodesic coordinates, G mu nu comma mu is equal to gamma mu nu comma nu. But then since these are local coordinates, we expect that to reduce to that of the equation to reduce to that of special theory of relativity, which says that T mu nu comma mu is equal to 0. Sorry, this should be, so this should be equal to 0. So in local coordinate system, that is in the geodesic coordinates, we have the equation satisfied by the energy momentum tensor to be equal to T mu nu semicolon mu equal to 0. And this is because in geodesic coordinates, this is exactly equal to this T mu nu comma mu, but the energy momentum tensor should satisfy the same equation as in special theory of relativity in the local coordinate system, local inertial coordinate system, which says that T mu nu comma mu is equal to 0, and therefore in geodesic coordinate system this is true. But then this is a tensor equation, and a tensor equation and therefore invoking the minimal coupling principle, we would say that this should be valid for the curved spacetime also. And since this is a tensor equation, this remains, this retains its form in all coordinate systems as well. And we take this to be the generalization of the conservation of the energy momentum tensor. So now we have two quantities. One is following from the Bianchi identity satisfied by the Einstein tensor, leading to this equation, which says that the covariant derivative of r mu nu minus half g mu eta, r mu eta minus half g mu eta times r is equal to 0. Now, the quantity on the left-hand side involves Ricci tensor and Ricci scalar, which involves second derivatives of the metric tensor, and therefore are apt to be replaced by the left-hand side of this equation in the proper Newtonian limit. And the right-hand side involves matter given by the density of the mass density of matter there. And in special theory of relativity, the mass density is given in terms of the energy momentum tensor. And we have a generalization of energy momentum tensor to the generalization of the conservation law followed by the energy momentum tensor to the curved space-time, and that's given by T mu nu semicolon mu is equal to 0. So adding this equation and this equation, we can write r mu nu minus half g mu nu r semicolon mu plus T mu nu semicolon mu is equal to 0. Even if we multiply it by a constant quantity, say k, this still is 0, and therefore taking the sum of these two is again 0. But this covariant derivative is linear, and therefore we may write this as r mu nu minus half g mu nu r plus k T mu nu mu equal to 0. So that means r mu nu minus half g mu nu r plus k T mu nu is either 0 or a constant whose constant tensor whose covariant derivative with respect to mu will lead to 0. So Einstein proposed an equation which said that this is equal to 0, leading to an equation of this following form: r mu nu minus half g mu nu r equal to minus k T mu nu. Now this equation has a similarity with the Newtonian equation of gravity, because on the left hand side we have a tensors involving second derivatives of the metric tensor, and in the Newtonian limit, as we have already seen, the second derivative, the metric tensor is what is related to the gravitational potential, and the Newtonian gravity equation is del square phi is equal to 4 pi g rho. So we can generalize this term to a tensor of this form. Now this involves second derivative of metric tensor in the Newtonian limit of the geodesic equation, and this also involves second derivative of gravity, and this contains the mass density which is related to the energy momentum tensor, and that is what we have here on the right hand side. So we may think of the generalization of this equation in terms of an equation like this. So Einstein has proposed this equation, and we should now check that in the Newtonian limit this equation reduces to the Newtonian equation of gravity. Before proceeding further, we also note that using the metric tensor we can lower the indices of these tensors. So we will have r mu nu minus half g mu nu r equal to minus k t mu nu, where a tensor like r mu nu can be obtained by using the covariant metric tensor as g mu alpha, g nu alpha, g mu beta, r alpha beta. Similarly, the energy momentum tensor as well. So that is this equation. We now consider the Newtonian limit of this equation. First of all, we consider a perfect fluid, and the energy momentum tensor of a perfect fluid, as we have already seen, is given by P by C square plus rho times U mu U nu minus P G mu nu, where P is the pressure that is measured in the rest frame of the fluid element, and rho is also the density measured in the rest frame of the fluid element. U mu, U nu are the components of the force velocity that is defined in the curved space-time, and G mu nu correspond to the metric tensor. We now restrict ourselves to the simpler case where the pressure of the perfect fluid is 0. So in that case, the mass distribution will be called dust, and the energy momentum tensor reduces to the simpler form. Since P is 0, this simply becomes rho U mu U nu. This term and this term becomes 0. And in the Newtonian limit, we have the following form. The contravariant metric tensor, as we have already seen, is given by eta mu nu minus h mu nu, and G44 is equal to 1 minus H44. That is because G44 is equal to eta 44 minus H44, but eta 44 is 1. So 1 minus H4. Now this object H mu nu is related to H alpha beta using the following form, following equation: eta mu alpha, eta nu beta, H alpha beta. So H44 would be eta 4 alpha, eta 4 beta, H alpha beta. But we have already seen that the Minkowski metric eta is diagonal. So that means only when alpha equal to 4 is this non-zero, and in that case eta 4 is 1. Again here eta 4 beta will be non-zero only when beta is equal to 4, and in that case it is 1. So we have only one term surviving from this, corresponding to alpha equal to 4 equal to beta. So the result is G44 is equal to 1 minus factor. Then this is 1, this is 1, this is H44. So H44. We now consider the frame of reference in which the dust is at rest. So in that frame of reference, the velocity of the dust is 0. The spatial component of the velocity will be 0. So that means u1 equal to 0, u2 equal to 0, and u3 equal to 0. Further, we also note that the norm of the four velocity is c square. This is something that we have seen in special theory of relativity. It is also true in general theory of relativity because of the following: u mu is equal to g mu nu dx d u mu nu, and that is because u mu is equal to g mu nu u mu, but this is also equal to g mu nu u mu equal to dx mu by d tau times u nu equal to dx nu by d tau. So this is equal to g mu nu by g mu nu dx nu by d tau square, but g mu nu dx nu is equal to ds square, so divided by d tau square, which is equal to ds. So now ds square can be written as c square d tau square, and the denominator is d tau square. So cancelling d tau square, we have c square. So u mod square, which is the norm of the four velocity, which is written as u mu, is equal to c square. So that's what we have over here. Now, if we look at the left hand side of this equation, in the rest frame of the dust, we see that the spatial components are all 0. So that means unless mu is equal to 4 and nu equal to 4, one of these velocity components will either be 1, 2, or 3, in which case the product will be 0. So the only surviving term in the sum on the left hand side is when the term corresponding to mu equal to 4 equal to nu. So the left hand side can be written as G44 U4 square equal to C square. The right hand side is C square. So G44 is 1. G44 is not 1. G44 is a metric tensor in the curved space-time. So now U4 can be taken as C divided by square root of G4. And that's what this is. Now G44 is actually 1 minus H44, and therefore U4 is equal to C times 1 minus H44 to the power minus. Now we have seen over here that T mu nu equal to rho u mu u nu. So T equal to rho u mu, sorry, T mu nu, rho u mu u nu. Now when in the rest frame of the dust, ui are all 0. The spatial component of the velocities are 0, and only the non-zero component correspond to when mu equal to 4 and nu equal to 4. So all other cases, all other components of the energy momentum tensor will be 0. So the non-zero component in the frame of reference in which the dust is at rest is given by T44, and that will be rho U4 square. But we have already seen that U4 is equal to C times 1 minus h44 to the power minus half. So this will be equal to rho times c square by 1 minus h44. Now expanding this, we have this equal to rho c square into 1 minus h44 to the power minus 1. So expanding this, I'll get rho c square 1 plus h44 plus higher order terms in h square. Now restricting ourselves to the lowest order term in h, and that corresponds to 1. So we have the lowest order term for the energy momentum tensor is simply rho c square. Now the Einstein equation that we have derived earlier, we have obtained earlier, is given by r mu nu minus half g mu nu times r equal to minus cap k times t mu nu. Now I can define an inner product over both the indices mu and nu with the metric tensor. So I will have g mu nu r mu nu minus half g mu nu g mu nu r equal to minus k t mu nu t mu nu. And this is nothing but the Ricci scalar. So I have r here, and then this minus half, then this quantity where g mu nu is simply, if I consider the contraction, the inner product over the index nu, this is simply delta mu, and this is a contraction over these two indices mu and mu. So that is equal to delta 11 plus delta 22 plus delta 33 plus delta 44. But then each of them, this is Kronecker delta, and each of those elements, delta 11 is 1, delta 22 is 1, and so on, and therefore this will be equal to 1 plus 1 plus 1 plus 1, which is equal to 4. So this factor is 4 times r and minus k, and this is a contraction of an inner product over both these indices mu and mu, and that will result in a scalar quantity, and we will simply call it t. So t is defined to be equal to g mu nu t mu nu. So this equation now becomes r minus 2r equal to minus k. So this implies on the left hand side I have minus r equal to minus kt, or r is equal to kt. So the Einstein's equation now becomes r mu nu minus this factor of half, then g mu nu, then r is equal to k times t equal to, on the right hand side, k times t mu nu. I can take this to the right side, and I will have r mu nu equal to, taken to the right hand side, it becomes k is a common factor, k, then half t mu nu t minus this factor t mu nu, and that is this equation. So we have eliminated this Ricci scalar r in terms of the scalar obtained from the energy momentum tensor. So to find t, we now compute the following. G mu nu, so t is equal to g mu nu t mu nu, and we know the reason why we did this is because we can compute t from the expression for the energy momentum tensor that we got over here. And the only non-zero component is T44. So T is equal to G mu nu T mu nu, but the only non-zero component in the rest frame of the dust is T44. So the only non-zero term is G44 times T44. Now we have already seen that G44 is 1 minus H44, and up to the lowest order in H, we have already also seen that T44 is equal to rho c square. So T is up to lowest order in H is 1 minus H44 rho c square. So up to lowest order, we can neglect the order of H term, so that results in rho c square. So we can go back to this equation and use this expression for T and find R44. So R44 is approximately equal to K. So K times half G mu nu with mu nu equal to 44. So we have G44 then T minus T4. So that is R4. But now G44 is equal to 1 plus H44 and T is equal to rho c square, and T44, as we have just found out, is given by rho c square up to lowest order in H. So rho c square. So rho c square appears in the first and the second term. So I can write R44 as K times rho c square, then half of the remaining term is 1 plus H44 minus, here rho c square has been taken outside and therefore 1. So this is a term of order H, so that can be neglected in term of order 1. So the result of this would be neglecting this term, half minus 1, so minus half. So the result is minus half K rho c square. So up to lowest order in H, R44 is equal to minus K rho c square. So now we need to find what R44 is. Now R44 is defined via this equation, which is R4 mu 4 mu. But now we also note that R alpha mu beta rho, or sorry, eta, is antisymmetric under these two indices. So that means if these two indices are the same, that is, if we have a term like R alpha mu beta beta, this should change sign under the interchange of these two, but then this will still be the same. So that will be R alpha mu beta beta with a minus sign, which implies that this is equal to 0. And therefore R44, because these two indices are the same, should be 0. So in this contraction, I only need to consider mu equal to 1, 2, 3, because mu equal to 4 correspond to this term, which is 0. So I may write this as R4I for I, where I is equal to 1, 2, and 3. Now explicitly writing the expression for the curvature tensor in terms of the Christoffel symbols and their derivatives, we get gamma I 4I comma 4 minus gamma I 4 comma I plus gamma nu 4I gamma I nu 4 minus gamma nu 4 gamma I nu I. Now we make use of the fact that in the Newtonian limit, uh, the field is static. So that means the metric tensor uh, is independent of the time. So the derivative with respect to x4 of the metric tensor is 0. Now gamma involves the metric tensor, and therefore gamma also becomes 0. So sorry, the derivatives of gamma with respect to x4 also becomes 0. So gamma I for I comma 4 will be 0. So the remaining terms in this expression are these three, and we need to find, or we need to keep only the lowest order terms in h in these three. To identify those terms, we first note that the Christoffel symbols gamma, mu, alpha, beta are given by this expression half g mu nu, g alpha nu comma beta, g beta nu comma alpha minus g alpha beta comma nu. Then in the Newtonian limit, this metric tensor g alpha beta can be written as eta alpha beta plus h alpha beta. So that if I take the derivative with respect to x nu, this will become if I take alpha beta nu, I will take the derivative with respect to nu. I will get eta alpha beta comma nu plus h alpha beta comma nu. Or in other words, g alpha nu comma beta is eta alpha nu plus h alpha nu comma beta. Now this quantity eta is simply the Minkowski metric, and that is constant in the inertial coordinate system, and therefore this will be 0. So only term that is remaining is this. Or in other words, over here the only term that remains is h alpha nu comma beta. So that means the derivative of the metric tensor with respect to a spatial coordinate is at least of the order of h. And this object g mu nu is eta mu nu plus h minus h mu nu. So this is of the order of 1 because we have this factor of eta mu nu over here, and all these factors are at least of the order of h. So this is of the order of h, and this is of the order of 1, and therefore gamma mu alpha beta is at least of the order of h. Now we see that this is already 0. Now this is the derivative of gamma, so this is of the order of h. Each of these terms gamma are of the order of h, and therefore this term is of the order of h square, and this term is also of the order of h square. So the third and fourth terms are of the order of h square, and only the second term is of the order of h. First term is already 0. So the lowest order term in h in R44 is simply the second term, which is minus gamma I for 4 comma I. And this is up to order h. But now gamma I for 4 is simply given by half g I nu g for nu comma 4 plus g for nu comma 4 minus g for 4 comma nu. Now comma I means the derivative with respect to xi. So this whole term becomes minus half times d by dxi of this expression. Further, since in the Newtonian limit the metric tensor is taken to be static independent of x4, this term which involves derivative with respect to x4 is 0, and so is this term. So the only non-zero term comes from this term, and there is a minus here and a minus here, so together that becomes plus. So the result is plus half d by dxi gi nu times g44 comma nu. Now gi nu is equal to eta I nu plus h I nu. So up to lowest order in h, this can be approximated as eta I nu. So we may write this as half d by dxi eta I nu g44 nu. Now eta is a Minkowski metric, it's diagonal, so that means the non-zero, only non-zero term is when nu is equal to 4 in this sum. So this sum now becomes eta I times g44 comma I, because all other values of nu will lead to this being 0 and therefore the product being 0, the corresponding term being 0. The only surviving term is this. Now the summation over I has to be now written explicitly, because I appears in more than one place, more than two, no, yeah, so yeah. So I have written summation over I explicitly over here, and eta I, as we know, because eta is this diagonal metric with diagonal elements -1, -1 and -1 for the first three terms. So eta I is -1. So substituting that, we have this -1 coming in front. So minus half. Then this is d by dxi. Then g44i. And the summation over I has been written explicitly here. So minus half sum over I d by dxi of g44i. But g44i is equal to eta 44 plus h44 comma I, but eta 44 is 1, so derivative of this term with respect to xi is 0, and therefore this is equal to h44 comma I, and this now becomes minus half sum over I d by dxi of h44 I. Now what is h44i? This is equal to d by dxi of h44. So d by dxi of h44i is simply equal to d square by dxi square of h44. Now we have sum over I. So in that particular frame of reference, this is sum of the second derivatives of the spatial coordinates, and this is nothing but del square of h. So we have R44 is approximately equal to minus half del square h44 up to the lowest order in h. But while discussing the Newtonian limit of the geodesic equation, we have shown that it reduces to the Newton's equation. The geodesic equation reduces to the Newton's equation in the Newtonian limit only if h44 is equal to 2 by c square times 5. So we can substitute for h44 by 2 by c square 5 there. So this factor of 2 is gone. There is a 1 by c square term, and then there is 5 here. So R44 is approximately equal to minus 1 by c square del square 5. So this is what we will get. But now we have obtained another equation for R44, and that is this equation. So R44 is equal to minus half k rho c square. Also, we have got this equation which says that R44 is equal to 1 by c square del square 5. So equating both this, we have minus k rho c square equal to minus 1 by c square del square 5. Or in other words, del square phi is equal to half k rho c to the power 4. Now, this is the Poisson equation. But now the Poisson equation representing the gravitational field is given by del square phi is equal to 4 pi g rho. And here the Newtonian limit of the Einstein's equation led to del square phi is equal to k rho c to the power 4. So that means this should be equal to half k rho c to the power 4, so that the Einstein equation reduces to the Newtonian gravity equation in the Newtonian limit. So which means that 4 pi g should be equal to half k c to the power 4, or k should be equal to 8 pi g by c to the power 4. So we have fixed this constant k there in the Einstein's equation, so that it will reduce to the Newton's equation of gravity in the Newtonian limit. Now substituting this value for k in the Einstein's equation, we will have r mu nu minus half g mu nu times r equal to minus k t mu nu, but k is now 8 pi g by c to the power 4, and therefore this is the Einstein equation. Now we also had a second form of the Newton's equation, which was written earlier, and that is this equation: r mu nu equal to k times half g mu nu t minus t mu nu. So again, writing using the expression that we just got for k, that becomes r mu nu equal to, instead of k I have 8 pi g by c to the power 4, so times half g mu nu t minus t mu nu. Now in the absence of matter, we have t mu nu equal to 0, because rho is equal to 0, and therefore g mu nu, t mu nu, which was t, and since all elements of t are 0, this is also 0. So from this we can set this to be 0 and this to be 0, and we will get r mu nu equal to 0. So this is Einstein's equation in vacuum. And this involves, r mu nu involves a second derivatives of the metric tensor, and therefore this differential equation needs to be solved, and its solution depends upon the boundary conditions.